Question 4 is also from paper 1, 2018. We have an integral, no context, just evaluate the definite integral. So looking at this, it looks like we're going to use a u substitution here. I'd like to substitute out the x plus 2 to make that integrand look a bit better. So let's start with that. So we're going to have u is equal to x plus 2. Going through the process, differentiate with respect to x. So du by dx is just going to equal 1. And then we need to make dx a subject. So quite easily here we have du and dx are interchangeable. Du equals dx. All right, so we're going to use this and we're going to use this, and let's sub those into the integrand and see what happens. So we're going to be integrating from 0 to 2, and those are x values, of course. We mustn't forget that. And the integrand, I've got 2x, and then I'm going to have u to the power 1/2. Okay, it has to be in index form so I can integrate. And then the du and dx are interchangeable, so I have du, which brackets off the integrand. So I have a problem here because I've got x and u, which I don't want. I can't integrate with respect to two variables. I'm going to have to go back to my original substitution and rearrange it. So we're now going to see that x would be equal to u subtract 2. And now I can substitute this in as well for x. So let's do that. So going back to my integrand, I'm going to be integrating x values from 0 to 2. And then it's going to be 2 lots of u subtract 2. Okay. And then u to the power 1/2 du. Okay. Normally I'd move the constant out. So I'll just put some equal signs here. So bring the constant out to the front. Those are still x values. And then we're going to multiply out the bracket containing u minus 2 with the u to the power 1/2. Now, just to remind yourselves, if you have u to the power 1, multiplying by u to the power 1/2, that's going to give you u to the power 3/2. Okay, subtract 2u to the power 1/2. All right, and I will put brackets in this time. So that's going to be integrated with respect to u. Okay, just remind yourself that these are x values. We can't substitute those in until we've replaced x in our antiderivative when we've actually integrated it. Okay, so let's do the integration now. So this is going to be 2 lots of whatever we get. So we're going to add 1 to the power, divide by the new power. So I'm just going to do this quickly. We're going to have 2/5 of u to the power 5/2. Just quickly check that you agree with that, and then add 1 to the power, divide by the new power in the second term. So adding 1 will give me 3/2. Then that means I'm multiplying by 2/3. So I'm going to have negative 4/3 u to the power 3/2. No c because it's a definite integral, and we're evaluating between 0 and 2. But once again, those are x values, not u values. Okay. Right. So before we put in our x values, we need to replace u with x plus 2. So this definite integral is going to be whatever we get when we evaluate this. So it's going to be 2/5 x plus 2 to the power 5/2. Subtract 4/3 x plus 2 to the power 3/2. Okay, and now we can just say x is 0 and x is 2, and we can sub those in directly. Now, we've also got the 2 on the outside to make life a bit easier, because it looks like we're going to be working with lots of powers of 2 here. As you can tell from the right-hand side of the initial equation we were given, we've got 32, we've got 2, we've got √2. I'm going to multiply through by 2, just so we don't have that 2 on the outside. So maybe this will make it easier. I don't know at this stage. So our definite integral is going to be 4 over 5 x plus 2 to the power 5 over 2. Subtract 8 over 3 x plus 2 to the power 3 over 2 between 0 and 2. Okay, let's substitute everything in. So this is going to equal, I'm going to keep my big square brackets here. Okay, upper limit, so that's going to be 4 over 5. Now, if I do 2 plus 2, that's obviously going to be 4. So I'm multiplying that by 4 to the power 5 over 2. Okay, which is a nice number. And also, I'm going to be subtracting 8 over 3 multiplied by the 4 again, which is then raised to the power 3 over 2. Okay, that will give me my upper limit, and that will be a nice number, relatively speaking. We're then going to subtract what happens when we put 0 in. So this time on the lower limit, we're going to have 4 over 5 multiplied by 2 this time to the power 5 over 2. Okay, subtract 8 over 3. I'm just running out of space there with the 7, so I'm just going to put it there. So 8 over 3 multiplied by 2 to the power 3 over 2. Close that bracket and big square brackets. I actually didn't need the big square brackets. I'm going to remove those. They were there for when the 2 was on the outside, so I probably could have removed them earlier. Never mind. Okay, now let's have a look at some of these values. See if we can simplify this. So we've got 4 to the power 5 over 2. Now that, if we use our laws of indices, if we take the square root of 4, that's obviously going to be 2. 2 to the power 5 is 32. Okay, and then I've got to multiply that by 4 and divide by 5. Okay, so that's all right. So that's going to be 32. I'm just going to make a note of that. Then we've got 4 to the power 3 over 2. Again, that's going to be 2 to the power 3, which is 8. Okay, so that's going to be good. Now, on the right-hand side with a lower limit, I'm looking at the answer. We've got root 2's everywhere. It looks like the upper limit is going to give me a nice value, which will probably be representative of the 2 here. So I want to be writing the right-hand side in terms of root 2, which I can, because I've got 2 to the power 5 over 2 here. Now that is, if we just have a look at this for a moment, this is the same as saying, well, it's the square root of 2, but then raised to the power 5. Okay, so I hope that makes sense. In a similar way, the 2 to the power 3 over 2, that's going to be root 2 cubed. All right, so we can do something like that in a moment. Meanwhile, let's go back to the right-hand side and tidy that up. Now, you can do this on the calculator if you like. Let's just quickly have a think. So we're going to have 4 multiplied by 32. So if I double 32, that's obviously 64. If I double that, that's 128. So I've got 128 over 5. Subtract what is 64 over 3. So we can do that on our calculator, no problem. That's the upper limit. Now let's work on the lower limit. We're now going to have 4 over 5. Now, again, I've got powers of 2 here. I've got 4 and 8, which sort of stick out. I've got the 4 and the 8 there. So I'm going to write that as 2 squared over 5. Okay, multiplied by root 2 to the power 5. We've just said, subtract 2 cubed, okay, over 3, multiplied by root 2 cubed. All right, and then I'm going to close that bracket as well. So just sorting out the left-hand side here, we've got 128 over 5, subtract 64 over 3. Now, if we just do that quickly, we're going to get the following. That's 64 over 15. And looking at the lower limit, so we're subtracting, we've got powers of 2 here. Now, I can do even better than this. I can actually write 2 squared and 2 cubed as powers of root 2. Okay, so we're going to have root 2 to the power 4. Okay, over 5. Multiplied by root 2 to the power 5. Subtract root 2 to the power 6. Okay, so that 2 cubed is basically root 2 to the power 6 because it's 6 over 2, which is 3. Multiplied by root 2 to the power 3. And that one was over 3. Okay, so we're getting somewhere. It's starting to look like the answer. So we've got 64 over 15. Subtract. Now, let's have a look at our powers of root 2. We're going to have root 2 to the power 9 over 5. Subtract root 2. Now, we've got 6 plus 3. That's also to the power 9 over 3. So this is interesting. Now we've got 64 over 15. And just to sort of combine these fractions, we've got the same numerator, but obviously I'm going to have to multiply the denominators to get the 15 on the bottom. So this is going to be 3 lots of the first numerator, subtract 5 lots of the second numerator. So that's going to give me minus 2 lots of root 2 to the power 9. Okay. Right, now this is where we can start to finish up. So we've got 64 over 15 plus, now again, I'm going to write this as a power of root 2. We've got root 2 squared multiplied by root 2 to the power 9 over 15. Okay, and I'm just running out of space. Let's see if I can finish off here, which is 64 over 15 plus, now if you add the powers, that's going to be root 2 to the power 11. Okay. Now, root 2 to the power 11 is exactly the same as root 2 to the power 10 multiplied by root 2. Okay, and that's all over 15. Now, that means that if you do root 2 to the power 10, that's the same as 2 to the power 5, which is 32. So I've got 64 over 15 plus 32 root 2 over 15. Okay. Now, we can factor out a 32 over 15. And hey presto, you're going to get that. Right. Now, you might be thinking, do I really have to do all that working out? No, but you do have to put in a few steps to show that you understand what's going on. It's actually sufficient. Once you've done the integration step here, where you've got the x substituted back in, you've got the limits on there, you're ready to substitute in the limits, you're perfectly entitled then just to show how to sub in the limits. So, for example, if you show this step here, okay, it's then enough to take you straight to the answer, which is over here, okay? I just want to show you that you can actually do it just by using SERDS indices, okay? It is doable. There are many other options as well. You could also do this using integration by parts. You could also take a use substitution as root x plus 2, like that. So that would give you u squared equals x plus 2, and you can use implicit differentiation. There's various ways of doing it, okay? That's just one way. But please just look through that in some detail and make sure you understand each of the steps.